Well, the next topic we have to discuss is the solvent. On all the problems so far, I haven't actually been drawing the solvent in the starting materials. In all these problems so far, I haven't been including the solvents in the starting materials, just for simplicity. But the fact is that on organic chemistry exams, oftentimes the professors do write the solvents. Professors oftentimes do include the solvents in the starting materials, and it's important to understand how to think about those solvents so that you don't get confused when you're solving the problems. So let's start talking about what role solvents are going to play in our solutions for these reactions. Do you know what a solvent is? I hope you know that the solvent is the liquid that the other starting materials are dissolved in. The solvent is the liquid that the other reactants are dissolved in. If you have experience working in chemistry labs, you should have lots of experience with the idea that most chemical reactions happen in a liquid solvent. Well, now is a good time just to become familiar with the common solvents that are commonly used at this point in the course. Here's some common solvents that are commonly used at this point in an Ochem class. It's a good idea just to become familiar with and kind of semi-memorize the stuff on this page. If you see any of the things on this page, you should be able to recognize that that is a common solvent. Maybe the most common solvent in chemistry is water. If you have any laboratory experience, I'm sure that you've done a lot of experiments using water as your liquid solvent. Some other common solvents are alcohols. Do you recognize why these are all called alcohols? An alcohol is an OH group connected to a carbon chain. An alcohol is an OH group connected to a carbon chain. Now is a good time to learn that definition. An alcohol is an OH group connected to a carbon chain. This could be called methyl alcohol. Here's another way to write methyl alcohol. This could be called ethyl alcohol. Here's another way to write ethyl alcohol. I'm writing this in a bunch of different ways because these are different ways that you might see this represented on exams. There are other alcohols that might also possibly be used as solvents, such as propanol, propyl alcohol. So this is just some examples. These are just a couple examples of common alcohol solvents. And here's some other examples of common solvents used at this point in the class that you should now pause the video and become familiar with. You should know that Me stands for a methyl group. Et stands for an ethyl group. So again here the Me subscript 2 stands for two methyl groups. So this and this both represent the same structure with two methyl groups on the nitrogen. Again, this and this both represent the same structure. This and this both represent the same structure. All right, I hope you actually paused the video and tried to familiarize yourself with these. Hopefully if you saw any of these structures or names, you would recognize that you were looking at a common solvent. There are certainly other solvents that you will see in your Ochem class. This is just a good list to get started with at this point in the course. Now, what role would we expect these solvents to play in reactions? Well, first of all, we can just say that they're playing the role of solvent. We can think of solvent as being a role, but that's not a role that you have to draw any electron pushing arrows for. You don't have to draw any electron pushing arrows if something is just playing the role of solvent. So we have to ask, will these play any other roles? In particular, right now we have to focus on, could any of these solvents be used as a nucleophile, say? Now, this is a little complicated. Some of these solvents can play a role in reactions. Some of these solvents can play a role in reactions. For example, some of these can be nucleophiles. But the rule is we generally will only use the solvent in the reaction if there's nobody else around who's more reactive. The general rule is that we're only going to use a solvent to participate in the reaction if there's nobody else in the starting materials who is more reactive. You should usually use the solvent as a participant in the reaction only if there's no other starting material that could be more reactive for that role. There are some exceptions to this rule that you'll have to learn about later in the course. Let's just try to be more specific here. Generally, these are the molecules that you might use in reactions right now. You could use water or an alcohol in a reaction, because you can see from this table that water and alcohol with a neutral oxygen are poor nucleophiles. Water and alcohol with a neutral oxygen are poor nucleophiles. They're poor nucleophiles, but you can see they're good enough for SN1 and E1. Water and alcohol are poor nucleophiles, but still good enough for SN1 and E1. So you will be using water and alcohol solvents sometimes for SN1 and E1 reactions. But you should only do that when there's no better nucleophile around. You should only use these poor nucleophiles if none of these good nucleophiles are around. You should only use these poor nucleophiles if this good nucleophile is not around. So that's the rule you should learn now. You will sometimes have to use water and alcohol as a nucleophile or a weak base for SN1 and E1, but you should only use water and alcohol in those roles at this point in the course if none of these good nucleophiles is present. You will learn an exception to that later in the course, but that's a good rule for right now. So let's try to be more specific about these solvents. You will sometimes have to use water and alcohol in SN1 and E1 reactions. You will sometimes use water and alcohol in SN1 and E1 reactions, but you will only do that if there's no better nucleophile or base present. And remember that the nucleophiles and bases that are better are listed in that table. On the other hand, I think that we would almost never use these solvents in SN2, SN1, E2, or E1 reactions. So we're not expecting to use these solvents in any of the reactions at this point in the course. At this point in the course, you should generally assume that if you see one of these solvents, it will not participate directly in the reaction. Later in the course, you will learn some important reactions using acetone. You will learn important reactions using acetone later in the course, but you probably won't need to worry about that right now. So at this point in the course, if you see one of these solvents, you can generally assume that it won't participate in the reaction. In particular, they won't participate in these 4 reactions. Again, you might want to pause the video and familiarize yourself with or memorize these ideas that I've written down about the solvents. Now let's practice this material that we've been learning about solvents. Please pause the video and try this problem. Now we'll discuss it. I'll start by numbering all the carbons. Now we look for ionic bonds so we can put in some charges. Well, because of the metal sodium, there's an ionic bond here between the sodium and the iodide. Positive sodium and a negative nonmetal iodide. Now we want to identify the roles. We would expect that because of the negative charge, this iodide can play the role of nucleophile. And because here we have a positive charge on a metal, metal, we expect to be a spectator ion. Now, what about the DMSO? Well, we've memorized that DMSO is one of the common solvents. So we know that one role that this compound is going to play is solvent. Do we expect it to also play a direct role in the reaction? No, because we've memorized that DMSO is one of these solvents that do not tend to participate in these types of reactions. So we do not expect DMSO to actually participate in the reaction based on what we've learned. It's in this category. So we don't expect the DMSO to directly participate in the reaction. Because it's attached to the bromine, carbon 1 will have a delta positive charge. And that will make carbon 1 into a reasonable electrophile. The neutral bromine, we've memorized, can be a good leaving group. The neutral halogen is the leaving group. The negative halogen is the nucleophile. Carbon 1 should be labeled as the alpha carbon because it's the carbon that's attached to the leaving group. So notice that the DMSO is not playing any direct role in the reaction. It's just a spectator as the solvent. Now we have to determine the mechanism. Well, carbon 1 is a secondary alpha carbon. Remember that the two different paths around the ring are counted as two separate carbon chains. So this clockwise path around the ring is counted as one carbon chain attached to carbon 1, and the counterclockwise path around the ring is counted as a second carbon chain attached to carbon 1. So we count two carbon chains attached to our alpha carbon for a secondary alpha carbon. With a secondary alpha carbon, that puts us in the middle row of our table. And our nucleophile, remember, is the I-, which puts us in the middle column of the table. So we decide the outcome is SN2. Notice that we didn't have to use the solvent to determine the type of mechanism. The type of mechanism here is not based on the solvent. It's based on the type of alpha carbon and the fact that we're using I-. Remember, we always want to write down the name of the mechanism. Now we can draw the mechanism with the electrons moving away from the nucleophile, which is the electron donor, towards the alpha carbon, and the leaving group will leave the alpha carbon. Now, did you notice that this problem actually doesn't require you to draw the mechanism? It's just asking for the product. Nevertheless, you should still draw the mechanism because the mechanism is our tool for drawing the correct product. Even if the problem doesn't ask you for the mechanism, you should still draw the mechanism because that's our major tool for getting the product correct. We want to continue to number all the carbons in this product to help us draw the pattern of the carbons directly. So the iodide is going to form a bond to carbon 1. Now, the iodide has to come in from the side opposite to the leaving group. Since the leaving group was in front of the page, the iodide will attack from behind the page, which leaves the iodide on a dash. And because this is the first arrow, we change the charge on the iodide from negative to neutral. The iodide is no longer ionically bonded to the sodium because the iodide has lost its negative charge. So the simplest thing to do is we just don't draw the sodium at all in the products, because that's just a spectator. This arrow tells us to break a bond to the bromine and also to change the charge on the bromine to negative. Because this was SN2, we inverted the configuration at carbon 1. Should we also invert the configuration at carbon 3? No. Carbon 3 is not participating in the reaction. Since carbon 3 doesn't participate in the reaction, there's no reason to make any changes around carbon 3. So carbon 3 will retain its original configuration. We only invert the configuration at carbon 1 because carbon 1 is playing the role of the alpha carbon in this SN2 reaction. Now remember, the problem was just asking for the product. So suppose there was a box where we were supposed to draw the product. If there was a box where we were supposed to draw the product, you'd probably be expected just to draw this in the box. The professor probably doesn't care much about this product. The professor probably cares about this product. So I'll just put this in the box. Again, the problem doesn't require you to draw this mechanism, but you still should draw the mechanism to help you get the correct product. And also, by the same token, although you're probably not required to write down the Br-, you should, at this point in your Ochem studies, you should write down the Br- for your own benefit, just so you're understanding the mechanism. You should write all the products just so that you're understanding the mechanism, but for your official answer to the problem, the professor is probably just expecting this. At this point in the class, you should almost always draw the mechanism for each reaction, even if the problem doesn't specifically require you to draw the mechanism, because the mechanism is our tool for understanding what's happening in the problem and for getting the product correct. Okay, so this problem gave us some practice with what do you do when the solvent is drawn. So first of all, you should have memorized that DMSO is a common solvent, so you can recognize this as a solvent. And you should also have memorized that DMSO is not going to be participating in these types of reactions. So when we see DMSO, we don't expect it to play a role in the reaction directly. And it doesn't affect, the fact that this is the solvent doesn't affect how we use the table to determine that this is an SN2 reaction. Please pause the video and try this problem. Again, we will number all the carbons. Again, we will assign the charges based on the ionic bond. Whoops. Now we want to assign the roles in this reaction. Now we see here water. Well, we know that one role that the water will play is the solvent. The water is the solvent in this reaction, but can the water play any other role in this reaction? Well, we have learned that sometimes water can be a nucleophile. Water can be a nucleophile, so should we say that the water will be the nucleophile in this case? Well, remember what we've learned. We're only going to use water or alcohol as a nucleophile if there's nobody better. Well, it should be pretty obvious that in this case there is somebody better, the I-. Remember, our I should always move to the formal charges. The atoms that are most likely to participate in the reactions are the atoms with the formal charges. So we actually will expect that the water won't be the nucleophile, the I- will be the nucleophile. Because the I- is a better nucleophile than the water. We've seen that water and alcohols can be used as nucleophiles, but generally only if there's no better nucleophile in the starting materials. Well, I- is a better nucleophile than water, so we will use the I- as the nucleophile, and we will not use the water as the nucleophile. How do we know that I- is a better nucleophile than water? Two ways. First of all, the I- has a negative charge, and the water is neutral. Things that have a negative charge are usually more reactive than things that are neutral. How do we know the water is neutral? Because the water is completely covalently bonded. And remember, when something's completely covalently bonded, we can generally assume that it has no formal charges unless they were already drawn for us. So we expect the I- to be the better nucleophile than water, because I- is negative and water is neutral. And there's another way that we know that I- is a better nucleophile. We have memorized this table, and this table tells us that water is a poor nucleophile and I- is a good nucleophile. So from the table, we also know that water is a poor nucleophile, while I- is a good nucleophile. Therefore, I- is a better nucleophile than water. The iodide here has the delta positive charge because it's attached to bromine. So again, we expect carbon 1 here to be the electrophile and the neutral bromine to be the leaving group. This is our alpha carbon. It's a secondary alpha carbon, so we're in this row. And again, we're using I- as the nucleophile, so we're in this column. So we predict the reaction will be SN2, and we should write that down. Notice how crucial it is to pick the correct nucleophile here. Because the nucleophile is I-, we're in the middle column, where the mechanism is SN2. If we were using water as the nucleophile, we would be in the left-hand column, and we would predict the major reaction would be SN1. So you can see you'll get a completely wrong mechanism if you use water as the nucleophile rather than I- for this problem. So the water really isn't playing any role in this reaction at all, besides being the solvent. The water is just the solvent, and otherwise it's a spectator. And now this reaction should look very similar, almost identical to the previous reaction. We have the same mechanism and the same product as in our previous example. So here's our answer to the question. So if you compare this example with the previous example, the difference between these two examples is that in this example the solvent was DMSO, and in this example the solvent was water. But you can see that for these particular problems, changing the solvent had no effect on our answer. With neither the DMSO nor the water ended up directly participating in the reaction. Neither of changing the solvent didn't change what the major mechanism was. The table tells us that the major mechanism is SN2, regardless of whether we use the DMSO or the water solvent, because all the other aspects of these reactions are the same. All right, so this gives us some more practice with how you handle a problem that tells you the solvent. Notice that both of these problems are much easier to handle if you have memorized that DMSO and water are both common solvents. Please pause the video and try this problem. I'll start by putting in some numbers. Next, we should look for ionic bonds so we can assign formal charges. But did you notice that there are no ionic bonds in these starting materials? All the atoms are non-metals. There are no metals. There are no metals such as sodium or potassium in these starting materials. So everything is non-metallic, and that means everything is covalently bonded, and that means that we don't need to add any formal charges. We can assume all the formal charges here are 0. So now we want to figure out the roles that atoms are going to play in this case. Well, what role do we expect the water to play here? Well, we know that the water is the solvent. We know the water is the solvent, but can the water play any other role? Well, remember that we've learned that water can be a nucleophile. We've learned that water can be a nucleophile. Should we use the water as a nucleophile in this reaction? Well, remember, we can use water as a nucleophile, but only if there is no better nucleophile. So we can use the water as a nucleophile, but first we have to check whether there's anything better to use as a nucleophile in our starting materials. Well, we should definitely check to see if anybody has a negative formal charge. Anybody with a negative formal charge would likely be a better nucleophile than water. But again, there are no negative formal charges in these starting materials. There's no negative formal charges, so we can't find any negatives to be a better nucleophile. And in fact, there's nobody around who's a better nucleophile than water. Remember, a Br- would be a good nucleophile, but this is a neutral bromine. Neutral bromine is not nucleophilic at all. Notice that neutral bromine doesn't even appear in the columns of the table. Neutral bromine doesn't even appear in the columns of this table, which is an indication that we don't expect neutral bromine to be nucleophilic at all, at least not for this type of reaction. The only other things we have here are neutral carbons and neutral hydrogens. Well, there's no neutral carbons or neutral hydrogens used as nucleophiles in this table. So it doesn't look like there's anything better around than the water. So in this case, we actually are going to use the water as the nucleophile. To be specific, remember to focus on the atom. We're going to use the oxygen as the nucleophile. It's the oxygen in the water that's the nucleophile. It's the oxygen in the water that's the nucleophile. It's only a poor nucleophile, but there's nobody better around, so we really are going to use the water as the nucleophile in this case. The bromine, neutral bromine, we know neutral bromine is a good leaving group, and because it's attached to the leaving group, carbon 1, I'll say is our alpha carbon, because it's attached to the leaving group. Now we want to pick a cell of this table. Well, here we again have a secondary alpha carbon. Carbon 1 is secondary, which puts us in the middle row of the table. And remember, we're using water as the nucleophile, the neutral oxygen in the water as the nucleophile. So we're going to be in this column. We're using the neutral oxygen in water as the nucleophile, and that tells us we're in this cell where the major reaction will be SN1. So we expect that the major reaction here will be SN1. Now, this problem just asked us for the name of the mechanism. So I'll just say that the answer to the question is the name SN1. Since our goal in this video series is not to learn how to draw the SN1 mechanism, so I won't bother to draw it. I'm not going to actually draw the SN1 mechanism here. I'll just answer the question by saying the name of this mechanism would be SN1. So what role is the water playing in this reaction? Well, the water is the solvent, but in this case, the solvent is also acting like the nucleophile. Sometimes the solvent can act like a nucleophile. So the water is playing two roles. It's correct to say that the water is the solvent, and it's also correct to say that the water is the nucleophile for this SN1 reaction. Water is only a poor nucleophile, but since there's nobody better around, we have to use the water. And even though it's a poor nucleophile, water is good enough for an SN1 reaction, as you can see from the table. So I hope that you will compare this example and the previous example. Notice these examples look quite similar, but they have different mechanisms. In this case, there was a water solvent, but we did not use the water solvent as the nucleophile because there was a better nucleophile, the I-, and the I- put us in the middle column and gave us an SN2 reaction. In this example, again, we had a water solvent, and in this case, we did use the water solvent as the nucleophile because there was nothing better. There were no better nucleophiles present. So in this case, we did use the water as the nucleophile, and as a result, we got that, that put us in the left-hand column and told us that the reaction was SN1 rather than SN2. So carefully compare and contrast this example where we did not use the water as a nucleophile, and this example where we did use the water as a nucleophile. One lesson we learn here is that you can't use the table until you've decided who the best nucleophile present is. It's useless to go to the table until you decide here that we're using I- as the nucleophile. It's useless to go to the table here until we decide we're using water as the nucleophile. You have to know who you're using as your nucleophile before you can decide which column of the table you're going to be in. So make sure that you're still in the habit of always predicting the roles that the various elements will play. Please pause the video and try this problem. Now we'll discuss. I'll start by numbering the carbons. We want to identify the charges. Well, here's sodium in an ionic bond with sulfur. So sodium is a metal from the left side of the periodic table. Sulfur is a nonmetal from the right side of the periodic table. Here is sulfur on the right non-metallic side of the periodic table, and sodium's all the way on the left. So we expect an ionic bond between sodium and sulfur. Since the sulfur is further to the right, it wants the electrons more. The sulfur will pull the electrons towards itself and end up with a negative formal charge, and the sodium will lose electrons to have a positive formal charge. All right, and now notice there are no other ionic bonds. In particular, notice there are no ionic bonds in this compound. Sometimes people think that this oxygen has an ionic bond to the hydrogen, but no. Remember that hydrogen is similar to carbon in electronegativity. Hydrogen is a non-metal. A bond between two nonmetals is covalent. So this is all covalently bonded. We don't need to add any formal charges. This is a neutral oxygen. Okay, so what roles would we expect things to play? Well, starting here with the CH3OH, you should recognize that the CH3OH is an alcohol. This is an alcohol. You could call it methyl alcohol. Now we know that the alcohol is the solvent. Alcohols are solvents. But we also know that it's possible for alcohols to be nucleophiles. So should we use this alcohol as a nucleophile? No, because there's somebody better, the negative sulfur. So we're going to use the negative sulfur as the nucleophile because that's a better nucleophile than the alcohol. Alcohol can be used as a nucleophile, but only for this material when there's no better nucleophile present. How do we know the negative sulfur is a better nucleophile than the alcohol? Two ways. First of all, this compound has a negative charge, and this compound is neutral. We would generally expect the negative compound to be a better nucleophile than the neutral. Also, our table tells us who's better. Notice that alcohol is here in the poor nucleophile column. And here we have negative sulfur. We haven't talked about this before. This is the first example that we've had with a negative sulfur, but you can see that negative sulfur is here in the good nucleophile column. So our table confirms that negative sulfur is a better nucleophile than alcohol. So we expect the sulfur to be the nucleophile, and we expect that the only role the alcohol is going to play is solvent. Other than being the solvent, the alcohol will just be a spectator. Carbon 3 here has a delta positive charge because it's bonded to the iodide. So we would expect carbon 3 to be the electrophile, and the neutral iodide is the leaving group. So carbon 3 is our alpha carbon, and carbon 3 is a primary alpha carbon because carbon 3 is bonded to just one other carbon chain. With a primary alpha carbon, we're in the top row for primary alpha carbons, and S-, we've already discussed, S- is here in the middle column. So here we are in the middle column of good nucleophiles and weak bases. So top row, middle column, our table predicts an SN2 reaction. Make sure you write that down, an SN2 reaction. Now we can draw the mechanism. The electrons go from the nucleophile to the alpha carbon, and the leaving group will leave. Number your carbons. So this arrow tells us to form a bond between the sulfur and carbon 3. I'm going to form a bond between the sulfur and carbon 3. And because we're at the beginning of the string of arrows here, the sulfur will lose its charge. The sulfur started negative and it's losing electrons, so the sulfur will become neutral. Therefore, the sulfur will no longer be ionically bonded to the sodium. We won't draw the sodium at all over here. Should the sodium still be bonded to the hydrogen? Yes, because the sulfur-hydrogen bond is covalent. The sulfur-hydrogen bond is covalent. They're both nonmetals, and we should never break a covalent bond unless an arrow tells us to break it. Well, this arrow does not tell us to break the covalent bond between the sulfur and the hydrogen, because the arrow here doesn't start on the bond, it starts on the lone pair. So this would be a big mistake. You have to draw the hydrogen here. We also have the iodide product. Its charge has also changed. This arrow does tell us to break a bond between carbon 3 and the iodide. Now, probably the only product the professor would care about here is this one. What did we learn from this problem? Well, we got some more practice with solvents. This is the first example that we've done with an alcohol solvent. When we see an alcohol, we recognize that that's a solvent. We could use alcohol as a poor nucleophile, but only if there's no better nucleophiles present. Well, here there was a better nucleophile, so we did not use the alcohol as the solvent. Also, this is the first problem that we've worked on where we used S- as a nucleophile. So this gives you an introduction to the use of S- as a nucleophile. S- is in the middle column of good nucleophiles and weak bases. Please pause the video and try this problem. First, we can number all the carbons. Now, normally we would look for ionic bonds so that we can assign formal charges, but notice that in this problem, they've already indicated that this bond is ionic by showing the charges for us. The professor doesn't have to show the charges for you in an ionic bond, but occasionally they will. So in this case, they made the problem a little bit easier. They've already indicated that this bond was ionic by showing us the charges. We should have known this was ionic anyway, because it's between a metal and a nonmetal, but here the professor already has shown us this is ionic, and they've already put in the charges for us. So we can just go straight ahead and try to assign roles. It doesn't look like there's any other ionic bonds. All these bonds are covalent, and all the bonds here are also covalent. Everything in this compound is a nonmetal, so this is all covalent. By the way, do you know what Me stands for? You should know that Me is an abbreviation for a methyl group. So this is a methyl group, and these are two more methyl groups. So those methyl groups just contain a carbon and 3 hydrogens. So again, all covalent bonds. Now let's assign the roles. What role do we expect this compound to play? Well, it would be best if you've memorized that this is one of the common solvents. You should have memorized that this is actually DMF. This is one of the common solvents, DMF. Here is that common solvent, DMF. And the name is DMF, and here's the structure. Now you can see that DMF is one of these solvents that we don't expect to participate in these reactions. So besides the fact that this is a solvent, we just predict that this will just be a spectator. This will not be participating in the reaction. We've just memorized that's how this solvent works. This DMF will be the solvent. We don't expect it to participate otherwise in the reaction. We focus on the formal charges. Because of its negative formal charge, we expect the sulfur to be the nucleophile. A positive charge on a metal makes the sodium the spectator ion. Carbon 1 here is delta positive because it's bonded to the iodide. So we expect carbon 1 to be our electrophile, and we expect the neutral iodide to be the leaving group. Carbon 1 is the alpha carbon because it's bonded to the leaving group, so we have a secondary alpha carbon. carbon one is bonded to two separate carbon chains. The carbon chain that begins with carbon 8 in this direction, and a separate carbon chain that begins with carbon 2 in the other direction. With the secondary alpha carbon, we're in the middle row of our table, and S-, we've learned, is in the middle column of our table. S-, middle column. Good nucleophile, weak base. So we predict an SN2 reaction. Make sure you write down the name of the reaction. Now we can draw the arrows going from the nucleophile to the electrophile. Now we draw the product. Number all the carbons. This arrow tells us to draw a bond between the sulfur and carbon 1. Now, the sulfur has to attack from the side opposite the leaving group. The leaving group is in front of the page, so the sulfur has to attack from behind the page, which puts the sulfur on a dash. The sulfur is going to lose its negative charge because it's at the beginning of the arrows, and therefore it loses the ionic bond with the sodium. There's no need to write the sodium spectator in the products at all. Should the sulfur still be bonded to this group? Well, remember, this is a methyl group. The methyl group would be covalently bonded to the sulfur, not ionically. Remember, this is a methyl group, all nonmetals, and the sulfur is a nonmetal, so these are all covalent bonds. And we don't break covalent bonds unless they're at the tail of an arrow. Well, none of these covalent bonds are at the tail of an arrow. The tail is on the lone pair, not in a bond. So this answer is wrong until we draw in the methyl group. We have to put in the methyl group or our answer is wrong. The sulfur will drag the methyl group along with it into this product because the sulfur is covalently bonded, not ionically bonded to the methyl group. We break the bond with the iodide. This arrow tells us to break that bond. And the iodide will gain a negative charge. This is the product that the professor will probably care about, so I'll circle it. Okay, so we got some more practice here with solvents. Here we have the solvent DMF. This is a solvent that's not going to participate in these types of reactions. So the fact that they told us that this was the solvent really didn't have any effect on how we solved the problem. We also got a little bit more practice with S-, and we've learned what Me stands for. You should know that Me is an abbreviation for a methyl group. By the way, because Me is a methyl group, we could write the starting material differently. Instead of writing it as Me, we could write it as a CH3 group. There's a little advantage to that because it would let us number this carbon. Remember, we should number every carbon that we show, and then to be consistent, we could show that here's where carbon 10 ended up. So if you like, when you see Me, you can actually write that as a methyl group, CH3, and that has the advantage that you can then number that carbon. So this answer would be considered a correct answer. This would be considered a correct answer, and this answer is also correct. It's really just a matter of taste. Either of these would be fine. Also, we saw that sometimes ionic bonds will be indicated for you by the professor. Occasionally, the professor will already have shown the charges for you. And in that case, obviously, you can just accept that those are the correct charges. This is still an ionic bond. Again, remember, don't assume that, say, this is an ionic bond. This is really a bond between a sulfur and a carbon, two nonmetals. Please pause the video and try this problem. Now we'll discuss it. We'll number the carbons. Make sure that you number all the carbons, including this one. Now we'll see the ionic bond, which allows us to assign formal charges. Now we'll try to assign roles. Now, what role do we expect this acetone to play? Well, we've memorized that acetone is a common solvent, so we know this will be playing the role of solvent, but will it also participate in the reaction? Well, we've memorized that acetone does not participate in the types of reactions we're studying right now. We've memorized that acetone does not participate in the types of reactions that we're studying right now. So, nope, we don't expect the acetone to participate in the reaction. Instead, we'll expect the negative carbon to be the nucleophile because of the negative charge. Because of this bromine, carbon 3 is delta positive, which makes carbon 3 our electrophile. We've memorized that neutral bromine is a good leaving group, which makes carbon 3 our alpha carbon. Carbon 3 is a secondary alpha carbon because it's attached to 2 carbon chains, which puts us in the middle row of our table. Our nucleophile is the cyanide, Cn-, which appears in the middle column, which puts us in this cell, SN2. Make sure that you write down that it's a secondary alpha carbon and that the mechanism is SN2. And in the mechanism for SN2, the nucleophile attacks the alpha carbon and the leaving group leaves the alpha carbon. Number all your carbons. There should be a new bond between 3 and carbon 5. Now, the cyanide will attack from the side opposite the leaving group, which leaves carbon 5 on a dash. Carbon 5 also loses its negative charge, which means carbon 5 loses the ionic bond with the sodium. No need to draw the spectator sodium at all in the products. And we do not break the covalent bond between carbon 5 and the nitrogens. This is a covalent bond, so those bonds are not broken because there's no arrow telling us to break the covalent bonds between carbon 5 and the nitrogen. We know these are covalently bonded because they're 2 nonmetals. This arrow tells us that we're breaking the bond between carbon 3 and the bromine and also changing the charge on the bromine. The problem was to draw the product. Well, here's the main product that the professor would probably care about for this problem. Okay, so we've discussed how to handle problems that mention the solvent. We're ready to move on to our next SN2 related topic. Let's try a brief review quiz. First question, please pause the video and answer. When a nucleophile attacks an atom that is attached to a leaving group, from what direction or directions does the nucleophile attack? Here's the answer. The nucleophile will attack from the side opposite to the leaving group. We learned this in an earlier video. We didn't explain why this is true. You might find an explanation for this in your textbook. This is just a fact that we've memorized. Next question. When an SN2 reaction occurs at an alpha carbon that is a stereocenter, what will be the stereochemistry of the product? Here's the answer. The product of the SN2 reaction will have inversion of configuration at the alpha carbon. Now remember, this fact is the explanation for this fact. Because the nucleophile is attacking from the side opposite to the leaving group, we've seen that causes inversion of configuration at the alpha carbon. And remember, we've seen it's important that there's only inversion at the alpha carbon. There's only inversion at the alpha carbon. If the molecule contains other stereocenters besides the alpha carbon, the SN2 reaction will not invert the configuration at any stereocenters besides the alpha carbon because there's no reaction happening there. The SN2 reaction only inverts the configuration at the alpha carbon stereocenter. These are ideas that are both crucial to have memorized. They'll be very helpful on exams. In the next video in this series, we will work on our next SN2 related topic.